Howdy. This video is on how different elements react. Using what we learned about electron orbitals and periodic trends, we can actually predict how different elements react. And so after watching this video, you should understand that elements in the column behave alike because they have the same valence electron configuration. You should understand that the noble gas configuration is extra stable, and so elements tend to lose, gain, or share electrons to get the noble gas configuration. Using the periodic trends, you should be able to predict which element is actually the most reactive in a group in general. And so when we looked at the periodic trends, we saw that as we go up and to the right, the electrostatic attraction between the outer electron and nucleus increases. Remember, going from left to right, you're adding more protons to the nucleus, and so stronger attraction. Going down, electrons are going into shells with bigger ends, so farther away from the nucleus, and so going down, weaker attraction. And so if we combine those two things, as we go up and to the right, the electrostatic attraction between the outer electron's nucleus increases. Now, because the attraction increases, that means the size of the atom actually decreases. The ionization energy increases. Remember, ionization energy is the energy required to remove an electron from an atom ion in the gas phase. The electron affinity increases. The electron affinity is the energy released when an atom ion in the gas phase gains an electron. And the electronegativity increases as you go up and to the right. And so the size, ionization energy, electron affinity, and electronegativity are all related to the electrostatic interaction between the outer electron and the nucleus. Now, this trend, as you go up and to the right, the elements want the electrons more, is consistent with how we break up elements into metal elements and nonmetals. And so the red ones are the metal elements. They tend to react by losing electrons. They have smaller ionization energies. The blue are the nonmetals. They tend to react by gaining electrons. They have larger electron affinities. Now, when we looked at the electron orbitals, we saw that the valence electrons are the outer shell electrons. They're the electrons in the biggest shell, biggest end, and they dominate the chemical behavior. Most of chemistry is about the valence electrons. And so electron configuration for germanium, you notice that you got 2 electrons in the 4s and 2 in the 4p. Those are your valence electrons. Outer shell, biggest end, and so the 4th shell is your valence shell. Now, elements in a column have the same valence electron configuration, and the number of valence electrons is equal to the column number if you ignore the transition metals. And so alkali metals have 1 valence electron, alkaline earth 2, column with boron 3, column with carbon 4, column with nitrogen 5, chalcogens 6, halogens mostly 7, and noble gases 8 except for helium, which has just 2. Now, elements in a column tend to behave alike because they have the same valence electron configuration. And so, for instance, the alkali metal ions, atoms tend to form +1 ions. Remember, hydrogen is not a member of any group. And if they lose 1 electrons, then they get noble gas configuration. But the alkali metal ions are all relatively similar. They're all fairly soft, reactive metals. The alkaline earth metals also behave alike. They typically form +2 ions, and they also are fairly similar. Now, these 4 columns, they actually don't behave too similarly, because remember, on top you have the nonmetals. So like if you look at the chalcogen row, on top you have nonmetals, on the bottom you have metalloids. And so in these 4 columns, the elements actually don't behave too much alike. The halogens behave alike. They all form diatomics. They typically form -1 ions. And then the noble gases are all extra stable. They're not very reactive. There's only a few known compounds with xenon, only a few with krypton, 1 or 2 with argon. There are no known compounds with helium and neon. They're not very reactive because they're very stable. Now, because they're very stable, that means that electron configuration is very stable, and so elements tend to gain, lose, or share electrons to get the noble gas configuration. Now, it's referred to as the octet rule because most of the noble gases, all the noble gases except for helium, have 8 valence electrons. And so charges of common ions, the alkali metals, +1, because if they lose 1 electron, then they get noble gas configuration. The alkali metals typically form +2 ions because if they lose 2, they get noble gas configuration. The halogens, if they gain 1 electron, then they get noble gas configuration. And oxygen, sulfur, if they gain 2, then they get noble gas configuration. And so in general, or often, atoms want to gain, lose, or share electrons to get noble gas configuration. And again, that's referred to as the octet rule. And so alkali metals have valence electron configuration ns1. They have 1 electron in the s orbital, that's the valence. And again, they tend to form +1 ions to get noble gas configuration. They're soft reactive metals. They all react with water exothermically to form hydroxide. Exothermically means they produce a lot of heat. And remember, hydrogen is not a member of any group. It's not an alkali metal. And so the reaction with water looks something like this. You form the hydroxide plus some hydrogen gas. And so if you see this reaction, often you'll see a flame, and that's just the hydrogen gas burning. And the hydrogen gas gets burnt because it's such an exothermic reaction. Now it's kind of interesting. If we think about the alkali metals tend to want to react by losing electrons, and if we think about the periodic trends, the best at losing electrons should be francium. And so in general, francium is the most reactive element. Reactive alkali metal.
Potassium is the third metal in group 1A. Lower than both sodium and lithium on the periodic table, it is even more reactive with water. The valence electron lost by potassium upon reaction with water comes from a 4s orbital.
So the potassium is more reactive than the lithium because potassium is lower, and so it's easier for it to lose that electron based on the periodic trends.
Lithium is the first of the group 1A metals. It reacts with water to form lithium +1 ions, losing an electron from a 2s orbital. Compared with sodium and potassium, lithium reacts rather slowly.
And so alkali metals have the valence electron configuration of ns1. And so lithium has 1 electron and 2s for the valence, and sodium has 1s2, 2s2, 2p6, and then the 3s1. And so for example, when sodium loses an electron, then it gets the noble gas configuration of neon. The alkaline earth metals tend to lose 2 electrons to get noble gas configuration. And so for instance, magnesium has electron configuration 1s2, 2s2, 2p6, 3s2. But when it reacts to lose those 2 valence electrons, then it gets the noble gas configuration of neon. Now the chalcogens, again, you start with nonmetals on top, and then you go to metalloids. And so as a column, they don't really behave too much alike. They all do have the valence electron configuration of ns2 and p4. Oxygen and sulfur tend to gain 2 electrons, forming 2 minus ions. And so this is how they start. And then sulfur, if it gains 2 electrons, then it gets the electron configuration of argon. For the halogens, they tend to form -1 ions. And so if we look at chlorine, it starts out as 1s2, 2s2, 2p6, 3s2, 3p5. And then if it gains 1 electron, then it gets the electron configuration for argon. But the halogens are all very similar. The fluorine, chlorine, bromine, iodine all form diatomics at room temperature. Fluorine and chlorine are gases, bromine is a liquid, and iodine is a solid.
In this experiment, we are demonstrating the physical properties of the halogens. First, chlorine gas is produced in the left-hand flask by adding concentrated hydrochloric acid to potassium permanganate. The yellow-green chlorine gas is condensed when it contacts a cold finger in the right-hand flask. The bubbling cold finger contains dry ice in ethanol, which at -78 degrees Celsius is cold enough to condense the yellow-green gas to a yellow liquid. When bromine is poured from a bottle, red bromine vapor first emerges.
But bromine is one of the few elements that's actually a liquid at room temperature.
The flask has dark red liquid bromine at the bottom. It is filled with bromine vapor at room temperature because bromine boils at 58 degrees Celsius. When iodine is gently heated on a hot plate, It vaporizes to form a violet vapor, which condenses on the cold surface of the flask placed on top of the beaker. As the flask is removed, we see crystals of iodine sparkling in the light. Eventually, we see the iodine crystals, which have recrystallized on the flask. Iodine is a purple-black solid at room temperature.
And so the halogens all tend to form -1 ions. They all are diatomic. Fluorine, chlorine are gases. Bromine's a liquid at room temperature, and iodine's a solid. Now the noble gases have full subshells, so they're extra stable. They're not very reactive at all. There's a couple known compounds with xenon, a couple with krypton, 1 or 2 with argon. There are no known compounds with neon or helium. They're very non-reactive. And so they have advanced electron configuration of NS2 and P6, except for helium, which is just NS2. Now, an interesting question you could be asked is put the halogens in order of increasing reactivity. And so halogens are the column second to the right. Now, if we think about it, those are nonmetals that want to gain electrons. And so from the periodic trends, we know that the best at gaining electrons should be fluorine. And so fluorine is going to be the most reactive halogen in general, and acetine should be the least. Remember that hydrogen sometimes is put above the alkali metals, sometimes put above also the halogens, but it's not a member of any group. You could also ask, what is the most reactive alkali metal? Alkali metals tend to want to lose electrons. According to the periodic trends, the thing bottom to the left is best at losing. And so francium should be the most reactive alkali metal. Should be the best at losing electrons. I hope that was helpful.